So hi everyone. So welcome to the last meetup of this year. My name is Marc Joie. I'm the chief scientist at Zama. If this is the first time that you attend this meetup, so you should know that there is a meetup every month on topics around fully homomorphic encryption. So like privacy, private computing, stuff like that. Also before starting, so also I have a quick announcement. So as you may know, there is a conference every year. It's on FHE.org. So we started that conference last year. So this year, the conference will be held in Tokyo, Japan in March. And if you like to register, so that's already possible. So you have to go to FHE.org. Then you go to conference 2023, and you should find a link to register. Okay, so without waiting any further, so today we have the pleasure to have Taekyung Kim, who will introduce HEaaN, that is the FHE library that has been developed by Cryptolab. So Taekyung, the floor is yours.
Okay, thank you very much. Hi everyone. Welcome to my talk. Yeah, my name is Taekyung, and I'm team leader of the homomorphic encryption team at Cryptolab. So before I get started, I want to express my gratitude to the organizers for arranging this wonderful meeting. And please come to FHE conference. Okay. Yeah, it's very. I'm very delighted to be here and deliver a talk here today. Okay, without further ado, let's begin. Whoop. Okay. I divide my talk into 3 sections today. So I want to introduce you to Cryptolab, our company, and our team, and about the HEaaN library. So when it began and how it developed since then. And after that, I guide you to the HEaaN library. So we look at basic functionalities and bootstrapping and GPU acceleration facilities and HEaaN math. This is kind of add-on to HEaaN library. Yeah, and I introduce all of that. And after that, I present you about some applications of HEaaN library in our company. What we are doing currently, and actually it will be very fun because we are trying to make some real world impact. So yeah, I hope it will be fun to all of you too. Okay. Okay. So here's our motto: HEaaN frees data. So people these days, everyone is talking about data ages, but actually the use of data is very, as all of you may know, it's very restricted due to privacy concerns and privacy issues. And our company and I actually dream of some whole new world that we can use data freely without any privacy concerns. And the homomorphic encryption is I think it's the key technology to enabling this kind of new world. So this is our motto. Okay, and let me briefly introduce our company. So Cryptolab is a startup based in South Korea, and we are specializing in the R&D of homomorphic encryption. So actually, we really focus on research and developing stuff. So, you know, one of my daydream is actually consider homomorphic encryption as a human being, for example, or a guy or a girl. Then I think I imagine homomorphic encryption as teenager. It's very early stage of development. So when I recall my teenage, I failed a lot, and I made huge mistakes many times. I wanted to date the girl, but failed, and something like that. But actually, it also teenagers has also lots of potential to do a new stuff, and we can open up a whole new world from a slightest clue. So that's my daydreaming. That's my imagination. So homomorphic encryption, I think it's in the teenage age. Actually, when I before I joining, I was joining in the Cryptolab. I was a number theorist, and number theory is teenage is I don't know, ancient Greeks. So it's lot of gap between homomorphic encryption. yeah. I'm not dissing number theory. I really admire that, but yeah, homomorphic encryption is still very young and very promising. But things are not going to work anytime. So we failed a lot of things, but yeah, it's still improving. So yeah. So Cryptolab is founded in 2017 by Professor Chung Chun. He's the C in the CKKS homomorphic encryption scheme. So CKKS homomorphic encryption scheme is actually dealing with real numbers. So it's very suitable for real world data. So currently he is the CEO of the Cryptolab, and he's a founder. And we have original patents on the CKKS HE scheme and bootstrappings and related technologies. This is our IP. And as a product, we have our HEaaN library. This is what I want to introduce you today. HEaaN library, it's a very high performance software library, and it's basically implementing CKKS scheme. And it's licensed to IBM H layers. It's an SDK for doing multiple stuffs like machine learning and AI in the homomorphically encrypted environments. And we also have HEaaN private AI. This is a kind of our version of SDK, and there are lots of services. I will introduce them later, but for example, Kodongi, it's a COVID-19 contact tracing app. This is actually the world first HE app. You can download in your phone, and we have also some voting and survey services. Okay. So we have currently more than 40 employees, and amongst them, more than 25 PhD and masters in mathematics and computer science, electrical engineering, and information security. So we are still need more people having talents, and we have lots of things to do. And the funding, we up to now, we have 21 million venture capital funding, so it's well funded for now. And we are selected as a sample vendor from Gartner for 2 consecutive years. Okay, and it's our team, homomorphic encryption team. It's one of the actually there are 4 teams for now in Cryptolab. Homomorphic encryption team is our team, and I'm the leader. And we are responsible for pioneering research in multiple areas in FHE. So basic operations and bootstrapping, and hardware acceleration and security. And we are developing and maintaining the HEaaN library. It's written in C++. So there are C++ engineers and CUDA, so GPU engineers, and mathematicians and cryptographers in our team. And also there are lots of minor libraries. And so our group photo. Here's me, in the left, the most left. It's me. Yeah. My advice here is if you take a group photo, locate yourself at the center, because you look better than expected. So, but yeah, here's our team, and currently we have 10 members, including 2 interns, masters in math cryptography, computer scientists. Okay. So actually there is an open source library called HEaaN. The HEaaN is originally an acronym for homomorphic encryption for arithmetic of approximate numbers. This was the title of the original paper of the CKKS homomorphic encryption scheme by Professor Chun. But in Korean, HEaaN means an insightful view or insight. So there is a company, HE company, called Tune Insight. So it's basically Tune HEaaN. So in Korean, you have HEaaN means that you're very insightful. So it's very cool name, I guess. And as a software library, we began as a reference implementation of the original paper. This is called the SNU-Crypto HEaaN, and it's still open sourced, and you can find it. You can find it's a GitHub repository online. But after that, we took over its development and made lots of enhancements in performance and hardware acceleration and stuffs. So now HEaaN is kind of HEaaN is now used as a branding for our products. So we have HEaaN Math. It's a math functions add-on. I'll talk about it later, and HEaaN the SDK and HEaaN step, etc. Okay, so so this was the repository as SNU-Crypto, and now we have a new version of HEaaN, and right inside. So lots of things are changed, and lots of improvements were made. Okay, that's it. So that's our brief introduction of our Cryptolab and HEaaN library. And next theme is the guided tour to the HEaaN library. So I guide you to the HEaaN library. So this part is actually the most technical part, but I don't want it too technical. So yeah, let's begin. So basically, I want to introduce about the HEaaN library, about four things. So basic functionalities and bootstrapping, and the GPU acceleration, and finally HEaaN Math. So you can see some basic functionalities here. So we first can context generate context. So this is 2 functions. We can with these 2 functions we can generate context. So it's every cryptography library one need to do first is the context generation, and we have 2 functions. So we have some predefined parameter presets, so you can use from presets, or you can use in a customized way. So you can input the ciphertext dimensions and stuffs, so modulus size and something like that to generate the context. But yeah, we provide them some simpler way to generate context with parameter presets. So there are lots of presets here, not quite a lot, but we are still making new stuffs. So basically, we divide our parameter presets into two classes. So presets starting with F is a full parameters. So we can do multiplications indefinitely using algorithm called bootstrapping. And S beginning with S is a sum of parameters. This is a we can with these parameters we can do a fixed number of multiplications. And the VGTSD is a logarithmic dimensions of the ciphertext, basically, to 17 to 13. So actually, this VGTSD is very mysterious alphabets to be here, but actually this is from usual way to measure the size of coffee in usual Korean cafe. So V is venti, G is grande, something like that. So it's kind of inside joke. Actually, yeah, we have lots of parameter presets here. So some more functionalities I want to recap. Homomorphic encryptions multiplication, CKKS homomorphic encryption multiplications. So basically, if we have a two ciphertext, CT1 and CT2, and then these ciphertext in CKKS scheme actually have two components, CT0 and CT1. And the decryption of this ciphertext is obtained by taking inner product with 1 and the secret polynomial S. So basically the decryption of the CT1 is CT10 plus CT11 times S, the secret. And the multiplication in the CKKS homomorphic encryption scheme is we first do the tensor operation. So usually the fresh ciphertext has two components, but after tensoring, we have a new ciphertext with 3 components. And this is decryptable with inner product with 1 S and S squared. And after that, we do relinearization to change the form of the ciphertext into the usual form of two coordinate ciphertext. And after that, we need to do rescaling. So actually, this is kind of usual process for experts in homomorphic encryption. We are usually doing this, but for the users, it is very hard to follow this everything. But so in our library, we provide functionalities to each step. So tensor function and relinearize and rescaling. But we also have some multiplication function. This is a kind of direct multiplication from these two ciphertexts to the end result. So user can choose what they want, these functions. So if a user wants more refined way to do multiplication for optimization purposes or something like that, then they can use these 3 functions, and then otherwise the user can use this multifunction. So every functionalities, every basic functionalities in this HEaaN library is basically like this. So we try to provide a simpler way to do stuffs, and also some complicated and for optimization functionalities. So this is just an example, but also in CKKS homomorphic encryption, there is operations called rotations, and we also provide some optimized way to do lots of rotations at once. It's called hoisting. Yeah. So after this multiplication, basically, especially after this rescaling function, so in the CKKS homomorphic encryption scheme, one needs to add a noise at the LSB part of the message, like this small error E here. And after multiplication, the noise grows basically. So what rescale operation does is to strip off, to get rid of the some LSB part of the modulus in the ciphertext. So this is so-called our leveled homomorphic encryption, and we lost basically some amount of modulus. So basically multiplication consumes modulus. So if we start with a fresh new ciphertext, and after a certain time of multiplication, then we reach the point that we cannot do any further multiplication. So that's kind of very serious problem, because if we want to do evaluate some deep circuit, then it's very problematic. So the bootstrapping is an algorithm to renew this deteriorated ciphertext into nearly fresh one, so one can do multiplications indefinitely. So this bootstrapping is an algorithm. So basically, bootstrapping enables the fully homomorphic encryption in this case. And for CKKS homomorphic encryption scheme 2018, the Professor Chun and other colleagues actually found a way to do bootstrapping. It's called approximate bootstrapping, but yeah, it's called usually a bootstrapping. And yeah, with this bootstrapping technique, we can do a lot of multiplication. And our Cryptolab's main focus is one of our main focus is to refine and make improvements in this bootstrapping operation. So currently, this is our API for bootstrapping, and we have lots of options here and lots of functions. So basically, what we want to do is to provide the user the lots of options to do for different optimizations. So basically, the different optimizations for encrypted messages. So it's complex vector or real vector. Then we can do different bootstrapping algorithm to optimize the result. And the extended bootstrapping is for larger input value range. So it's one of our effort is meta BTS. This is very good result to improve the bootstrapping precision. It's called the meta BTS technique. And actually, the nutshell of this new algorithm is doing bootstrapping multiple times to improve precision. So if we have any kind of bootstrapping algorithm, then we can do it in multiple times to greatly improve our bootstrapping precision. So basically, from this n-bit bootstrapping, we can do it twice to make a 20-bit bootstrapping. And as a result, yeah, it's error. The error is very, we can control it as a very small error and yeah, it's basically improves the precision. And this kind of technique also can be used for doing bootstrapping in a multiple range. I mean, the bigger range. So this is actually bootstrap extended function is implemented. Okay, that's bootstrapping. And we also have a lot of, we are doing a lot of effort to acceleration, especially on the GPU. So currently we are, we have facilities to do GPU acceleration. So every operation in HEaaN library can be accelerated using NVIDIA CUDA capable GPUs. So as you can see, the same operation, the bootstrapping operation, and it's around 20x speed up in a single bootstrapping operation. This is measured with a GPU, using GPU and 8-threaded CPU version. So it's quite fast, but actually for using the GPU acceleration, the one of the very important thing is to remember is never think GPU acceleration like a kind of magic wand or panacea. So many people just think that if we do it in a GPU, then everything will be magically faster, but it's not, because we have a lot of typically in homomorphic encryption, we need a lot of very huge size of evaluation keys, and data is typically very big. So it is transferring the data from host to GPU or vice versa can take a lot of time. So basically, doing GPU acceleration is a very hard thing. We need some kind of expertise on this. So yeah, and actually for this we are doing a lot of research on this topic. So we are currently doing our research to offloading for using a lot of GPUs at once, and we also invest our time and effort to the compilers, so we can do bootstrapping or something, other operations, or evaluating big circuits more easily. Okay. Okay, in the HEaaN math, this is an add-on to the main library. So basically, lots of libraries out there, especially homomorphic encryption libraries, they just provide some kind of basic operations as a mathematical primitives like multiplications and addition, rotation, something like that. But in order to use the homomorphic encryption in a real world, we need more stuffs like comparison and mathematical functions, sorting, as I described here. And this is actually a basis. HEaaN math is actually a basis for HEaaN.stat, and HEaaN.ai, and HEaaN.ml. These things are actually our plan is to release HEaaN.stat in the March next year, where it basically HEaaN.stat. What HEaaN.stat does is to do statistical things such as averages and variances and lots of test functions in statistics. And this is actually HEAAN also is a basis for HEAAN.ai. What we want to provide is in HEAAN.ai is the AI training and inference stuffs and machine learning. So we have lots of layers in the HEAAN library. So HEAAN main library is at the base, and on top of that, HEAAN.math is the add-on. And our theme for the HEAAN library also is applied here. So we want to provide the users a lot of options to do in a general computing. In comparison and mathematical functions, and also sorting function is provided. Okay. Actually, you can download the Docker images of pre-built HEAAN library at HEAAN.it. So please go there and use it. And feel free to contact our team if you have any questions or comments. Okay. Finally, I want to show you about some applications of HEAAN library. So for the real world use cases, I want to introduce a few of the stuffs here. But first thing, in the credit score, so our problem is to build a credit rating using data from two different organizations. Here, two different organizations is first one is the Korean National Pension Service and the KCB, the Korea Credit Bureau. So in Korea, if I enter a company, if I'm employed in a company, then I am just automatically registered to a Korea National Pension Service. So I must pay some small rate of my payment into the pension service. This is for basically funds after I retire in a far future or near, I don't know, but yeah, that's basically Korea National Pension Service does. And KCB is a Korea Credit Bureau. It's unlike its name, it's kind of civilian running company. It's basically provide the credit scores to the banks if you want to get a loan from a bank. So basic idea on this stuff is if I pay the National Pension Service regularly and very well, then I have high tendency to have a high credit score. So that's our original assumption. So in order to prove this, we need to kind of joining data from NPS and KCB together and make a statistical analysis. But it was before homomorphic encryption, there was no way to do this because of the regulations, government regulations, because basically the data from NPS and KCB is highly confidential. But what we did is to do this statistical analysis with using logistic regression, with using homomorphic encryption. So training basically took 2 hours to do. But as you can see in this next slide, actually 550K people's credit score were actually increased after this service. So yeah, it's making real world impacts here. It's very, very good to see. Okay, and another thing, we have our assignment from Statistics Korea. This is basically National Statistics Office in Korea, and they provide us 9.1 million records. It's a syntactic data, but we could successfully compute the count and average and variance and stuffs. It's very in a very very fast, and another thing, we do a lot of stuff like text classification, image classification, and also DB search. So I'll show you about one of these examples later. So these are our commercial deployment. As I mentioned, the personal credit rating system, we actually made a real world impact. And the Kodongi is a COVID-19 tracing. It's a mobile app, and this is as far as we know, this is the only mobile app using homomorphic encryption. And nowadays, it's kind of is obsolete because it's with COVID situation. But daily active users. So at one day we recorded 100K DAUs. So basically, it is an app you can download in your phone, and this app is using GPU technology, GPS technology to record your locations, your tracks in your phone, and it send over to the server, but in a homomorphically encrypted way. And in the server, your trace is compared with traces from COVID patients. So it then tells you hey, you're contacted with a patient at some time, something like that. And another thing, we in Naver Cloud Platform, this is the largest cloud service provider in Korea, and we are providing a cloud-based HE as a service. And another thing, we are voting service, this online voting service without exposing users' choice. Yeah, these are our commercial deployments. As an example, I want to show you a transfer learning example. This is some background is needed because usually military departments and agencies have a huge amount of secret private data. It's highly confidential, of course, but also have limited capabilities on AI and ML. And HE actually enables possibilities for outsourcing this kind of data analysis in this case. So as a POC, one of the agencies actually contacted us and assigned us as a POC, and the basic task is to train a classifier to differentiate between images of military vehicles and images of civilian vehicles. And but they did not actually provide the images. It's highly confidential, of course, and so we scrapped around 1,000 images from the internet and 700 images as a training data. We basically do transfer learning. So transfer learning is for faster training and higher prediction power, and very efficient for small input data. So result is actually very good, but you should aware that it's basically because that the size of the image is so small, so 1K, so it's quite fast and very powerful. But I think basically it's in training, so it's maybe in a training in a 1 hour, maybe acceptable in the military services. So yeah, it's very good result. Okay, that's all of my talk. Thank you very much. And do you have any questions?
Thank you, Taekyung. So do you have questions for the speaker? So you can ask directly, so just unmute yourself and you could directly ask the question to Taekyung, sorry.
Yeah, I have one. Hi, thank you for the talk. Very interesting. Hi. I have a question related to compilation, because you mentioned that compilation is needed at some point to ease, the generation of the homomorphic application. Can you talk a little bit more about what you're trying to achieve in that space and how your compiler works? What is typically the input that is given by the user, what it does internally, what it outputs? Yeah, just wanted to have some more insights about this part.
About the compilers, you mean?
Yes. Yeah.
Yeah, actually, currently we do not have any compilers like but we are actually actively researching about that, with collaborating with lots of experts in this field. So basically, I can tell you, actually compilers, we have a lot of layers in the compilers. So I can tell you about the 3 layers of compilers we are currently researching. So first thing is to machine learning users. They want to write code using their preferred language like Python, and they are very accustomed with Python packages like scikit-learn or something like that. This is very very famous for machine learning engineers and data scientists, but actually they do not have lots of knowledge about homomorphic encryption. So in that case, we can provide a compiler to transform the code from this data scientist code into the homomorphic encryption code. For example, for HEaaN code. So that's one thing. And another thing is to related to optimize our HEaaN library. So it's a layer, very low layer, located in a very low layer. So we are developing using MLIR compilers. So we are developing a MLIR dialects called poly language. This is sole purpose of this poly language is to do polynomial operations fast. And yeah, we have compilers. We are developing compilers to transform the HEaaN code into this poly language, and its performance is very satisfying, but not yet ready. So yeah, these things are our main concerns. And another thing is about I mentioned earlier about the GPU offloading. So we are currently, our HEaaN library, we are mainly using a single GPU, but we can think of another situations like we have lots of GPUs in a computer and we want to use all of that at once. At the time, compiler can help about that. Yeah, that's it. Thank you.
Thanks.
Any other question, comment, remark?
Yeah, I have a question about the use of privacy for digital healthcare imagery, medical imagery. how do you see this happening? I mean, is it possible today? What is needed for it to become possible in the future?
Yeah, actually, in our company recently, we made another team for healthcare services. So I don't know much about these details here, but I think it's happening now. And actually, we are now collaborating with a lot of hospitals, big hospitals, university hospitals in Korea, to do to facilitate the use of HE in healthcares and medical imagery, something like that. So I think there's no visible result and now, but I think it's happening. And next year I think we can show you another things about that. Yeah, but I'm yeah, I don't know. I'm maybe I'm too optimal.
Thank you.
Any more question? Oh, there is one in the chat.
Yeah. In the chat there are some questions. First question from Mohammed. Do you have public documentations of commercial application? Yeah, HEaaN library is currently proprietary, and we only provide the preview binaries in the HEaaN.it website. And API documentation is in the website, but actually this is very unsatisfactory for now, because we need more documentation. It's very deep topic, homomorphic encryption. So yeah, we are trying to provide a lot more documentation in the future. And patenting update, CKKS scheme. Patenting make it harder for others to adopt the CKKS scheme. Yeah, that's exactly right. And yeah, it's kind of we don't have any plan to actually force this patent, to push this patent. So it's very important to grow the scene. But yeah, it's a kind of, yeah, I was just stating the state of our IP. So yeah. And final question, can you please elaborate on DB search using HEaaN? Yeah, actually, it's still developing about the DB search. We have some positive results, so DB search, but I think it is a whole another thing to do. We need to do a lot of things to do. Yeah, so it's kind of early to talk about the DB search for now.
Okay, so
yeah,
and wrap up. So thanks again, Taekyung, for the presentation. Thanks all for attending. See you next month, and I already wish you a very happy holidays.
okay.
Bye-bye.
Thank you very much.
Goodbye. Thank you, guys.
Thank you.